Welcome to The Explainer. Today we're jumping right into the fundamental physical rules that govern the materials we interact with every single day. Look, whether you're in engineering, product design, logistics, or you're just trying to optimize your daily workflow, understanding the physical constraints of matter isn't just basic science. It's really the absolute foundation of how we manipulate the physical world around us. We're talking material properties, practical volume changes, and exactly how particles move.
So, here is our roadmap for today. We're going to cover 1. The macro properties of matter, 2. Understanding particle movement patterns, 3. The mechanics of flow, and 4. The rules of compression.
All right, let's kick things off with Section 1, Macro Properties of Matter.
It's actually fascinating how neatly matter categorizes itself. Think about it. Solids maintain a very strict, fixed shape and volume. They will not compress, and they certainly don't flow. Liquids, well, they're a bit more adaptable. They'll take the shape of whatever container you put them in, and they can flow, but their overall volume stays stubbornly fixed. Gases, though, they are the ultimate rule breakers here. They adapt both their shape and their volume, they flow completely freely, and they are highly compressible. For any busy professional dealing with physical goods, this is basically your quick reference guide to material constraints.
But to truly leverage these macro constraints rather than just, observing them, we really have to zoom in. We need to look at the foundational framework of it all, which is particle theory. Now, this is the widely accepted scientific model stating that absolutely everything is made up of tiny, invisible particles. The real secret to a material's physical properties doesn't lie in what the particles are, but entirely in how those particles are arranged.
Which brings us to a really crucial operational question. Why does a gas effortlessly expand to fill an entire room, while a solid brick just sits there, completely unchanged under pressure? What is the actual mechanical difference happening beneath the surface?
That brings us to Section 2, Understanding Particle Movement Patterns. Let's see exactly how those microscopic arrangements dictate macroscopic reality.
Think of solid particles, kind of like a highly rigid corporate structure, or maybe tightly packed stadium seating. The particles are arranged in this fixed, highly precise pattern, and they're held together by incredibly strong attractive forces. Because they are locked in so tightly, they can't actually move from their designated spots. Literally, the best they can do is just vibrate right there in place. And that strict internal structure is exactly why a solid holds its shape so perfectly.
Liquids, on the other hand, are a bit more like a crowded networking event. The particles are still physically touching each other, so the room is packed, but the attractive forces holding them together are a lot weaker. This means that while they stay together as a collective group, they can actively squeeze past one another and swap positions. They're mobile, but they're still confined to the crowd.
And then we have gases. Gases are essentially like a few people wandering around a massive empty warehouse. The particles are spread a long way apart. They don't touch each other, and there are absolutely zero attractive forces holding them together. They just move freely and quickly in all directions, naturally spreading out all by themselves to fill up whatever space they're given.
Moving right along to Section 3, the mechanics of flow.
So the absolutely crucial point to grasp here is this. Physical movement at the macro level strictly requires mobility at the micro level. Matter can only flow, or be poured, if its individual particles actually have the freedom to move past one another. Because solid particles are completely locked in that rigid grid by strong forces, they physically cannot glide past one another, which means, simply, solids cannot flow. I mean, if you tip a bucket of bricks, they'll tumble out, sure, but they certainly don't pour. Liquids, with their much weaker forces, easily allow particles to slide past one another, which makes pouring possible. And gases? Well, possessing zero attractive forces between their particles, they don't just flow, they rapidly spread out in literally every possible direction.
Okay, let's dive into Section 4, the rules of compression. When you need to save space, pack materials, or engineer a pressurized system, you are dealing directly with these exact laws. The whole secret to compression really just comes down to a concept we can all easily understand: available real estate. It's all about the internal space between the particles. Gases feature these massive gaps between particles, whereas solids and liquids have particles that are already practically sitting right on top of each other. To put that into perspective, think about a standard syringe. If you fill a syringe with water, cap the end, and push down hard on the plunger, you hit a literal wall. You cannot physically force liquid water into a smaller volume. But if you do the exact same thing with a syringe full of air, the plunger glides down effortlessly, and you significantly shrink the gas's volume. Let's break down exactly why this happens.
Gases can be compressed simply because their particles are naturally a long way apart, with no attractive forces. When you push that plunger down, you aren't actually shrinking the particles themselves, right? You're simply closing the vast empty distances between them. Because there's so much empty space in there, the highly mobile particles gladly move closer together, which easily results in a smaller overall volume.
Conversely, trying to compress a solid or a liquid is basically like trying to add more cars to an already jam-packed highway. The particles are already touching, or they're incredibly close together, held tight by attractive forces. There is simply no physical room left for them to be pushed any closer. Because that internal real estate is completely maxed out, their volume remains fixed and unchangeable. Doesn't matter how hard you squash them.
And just as a fascinating side note to all this talk about particle density, what happens when you have zero particles? Well, a space completely devoid of any matter, no solids, no liquids, no gases, is called a vacuum. It contains absolutely nothing. And no particles means there is nothing to flow, and absolutely nothing left to compress.
Now, I want to end on a slightly provocative note that really applies this theory to the real world. We just firmly established that solids mathematically cannot be compressed, right? Because their particles are already touching. So I will leave you with this to ponder. How do you explain a standard kitchen sponge? You can easily squeeze a solid sponge down into a fraction of its size. So based on the particle theory we just covered, what is actually happening on a micro level when you squeeze it? Are you somehow breaking the laws of physics, or are you just squeezing out the vast empty spaces of a hidden gas? Think about that. Thanks for joining me on this explainer, and I really hope this gives you a much sharper lens through which to view the physical constraints of the materials you work with every single day.